This is the last lecture of this chapter on alcohols, ethers, and thiols. In this presentation, we will cover the following. We will continue the study of reactions of alcohols, which we started in the last lecture. Next, we will move into the structure and nomenclature and also the physical properties of another functional group called ethers. We'll do the same for thiols. And we'll also look at some reactions involving thiols. And lastly, we will look at the synthesis of important organic molecules, mostly alcohols, using the reactions covered in this lecture. So let us begin. Alcohols, as you will recall, they have the OH functional group. So let's look at the acidity. You may remember that an acid is defined as a proton donor. So in other words, an acid is a proton. Remember, a proton is H plus donor. So an acid, based on this definition, must have a hydrogen. And if it gives up that hydrogen in the form of H plus without its electron, it's an acid. Alcohols, as you've seen here, they all have the H for the OH. So therefore, alcohols are potential acids. The question now is, are alcohols strong or weak acids? As you can see here, the pKa of alcohols are about the same as water. You will recall that pKa is really a measurement of the acidity of molecules, the equilibrium constant. But we know that water is a very weak acid because we drink it every day. So if water is a weak acid and alcohols have the same acidity as water, alcohols are in fact weak acids also. There's a special alcohol known as phenols. So here it is. It's bonded to the benzene ring. But here is the hydrogen of the alcohol. For these molecules, phenols, this hydrogen here is acidic. Or should I put it this way? It's more acidic than alcohols. So that means that if it's an acid, it will react with a base, such as sodium hydroxide. You will recall that sodium hydroxide is a strong base. So the hydroxide anion here will react with the H here, because an acid is a proton donor, H donor, to form water, as you can see here. And what's left behind is a salt, a water-soluble salt, sodium phenoxide. So conclusion, alcohols are weak acids, but phenols are stronger acids and will react with a base such as sodium hydroxide or potassium hydroxide to form salt and water. The reactions that alcohols undergo are typically oxidation reactions. So let us define oxidation, and then let us apply that concept to the oxidation of alcohols. One definition that we learned in Gen Chem is oxidation is the supply of oxygen, and equally important in organic chemistry, it's the removal of hydrogen to produce another molecule. So it's removal of hydrogen and also the supply of oxygen. So let us look at this reaction here, hypothetical reaction. So here is a primary alcohol. Remember, we have classified alcohols as primary, secondary, and tertiary based on the number of alkyl groups or carbon-containing groups that are bonded to the carbon that has the OH. This is a primary alcohol because it has one alkyl group or carbon-containing group bonded to the carbon. Therefore, it has two hydrogens, one and two hydrogens bonded to this carbon. In the presence of an oxidizing agent, which will give you an example on the next slide, but in the presence of an oxidizing agent, it will remove one of these hydrogens, and you can see it's gone, and the oxygen and the OH group is oxidized to a carbon oxygen double bond. This functional group is called an aldehyde, as you will recognize from the carbonyl that's bonded to an H. Because this aldehyde has an H, it can undergo further oxidation by removing this H, based on the definition, to form a carboxylic acid. So notice again, this is oxidation because here we have introduced here another molecule or atom of oxygen, and we have also removed the hydrogen from the aldehyde. So primary alcohols can be oxidized to aldehydes, and in the presence of more oxidizing agent, the aldehyde can be oxidized to a carboxylic acid. So look out for these functional groups as products for these reactions. Let us look at a secondary alcohol. You may recall that a secondary alcohol has two carbon-containing groups bonded to the carbon that has the OH. In the presence of a strong oxidizing agent, which we'll cover in the next slide, the hydrogen here, shown in red, is removed. So notice it is gone in the product. In addition, the OH is converted to a carbon-oxygen double bond, oxidation. So the secondary alcohol, in the presence of an oxidizing agent, is converted to a ketone. Let's look at a tertiary alcohol. Tertiary here means that the carbon that has the OH group contains 1, 2, and 3 carbon-containing groups. Notice no hydrogens as we have here. So this has no hydrogens, just carbon-containing groups bonded to this carbon here. In the presence of an oxidizing agent, no reaction. Why no reaction? Because there is no hydrogen to be removed from a tertiary alcohol. So that's the concept. Let us apply that now to some real molecules. So here's an alcohol. Classification of that alcohol: it's a primary alcohol because it has a carbon that has the OH group and it has one alkyl group bonded to it, which means that it has two hydrogens. In the presence of an oxidizing agent as shown here. The name of this is sodium dichromate in sulfuric acid, a very strong oxidizing agent. It will remove both hydrogens and insert an oxygen here to make carboxylic acid as the product. So the oxidation of alcohols in the presence of sodium dichromate and sulfuric acid will give us a new type molecule called the carboxylic acid. Let's look at the secondary alcohol. It has two alkyl groups bonded to this carbon. Here they are, a propyl and a methyl group. This is a CH3, and here is a CH2, CH2, CH3. Equally important, it has just one hydrogen bonded to that carbon. This carbon right here that has the OH group. In the presence of a strong oxidizing agent, how do we know that's an oxidizing agent? It has lots of oxygens. Typically, an oxidizing agent has lots of oxygen atoms present. As you know, that oxygen is O2, so it is an oxidizing agent also. But sodium dichromate in sulfuric acid is an oxidizing agent. We have just one hydrogen here, and the product formed is a ketone. So the oxidation of a secondary alcohol in the presence of sodium dichromate and sulfuric acid gives us a ketone. Notice the same number of carbons are present. Here's the methyl group, and here is the same propyl group. It's just that we now have here a carbon-oxygen double bond, also known as a carbonyl, to form a ketone. Here's a tertiary alcohol. Why tertiary? It has 1, 2, and 3 alkyl groups bonded to this carbon. Notice no hydrogen atoms. So in the presence of a strong oxidizing agent, no reaction, because there is no hydrogen to be removed that's bonded to the carbon that has the OH group. Notice there are hydrogens here, but they are not bonded to the carbon that has the OH group. So therefore, no reaction for the tertiary alcohol in the presence of sodium dichromate and sulfuric acid. Here's some more examples. Here is another alcohol, menthol. It's a secondary. As you can see here, here's a carbon that has the OH group. It has a hydrogen bonded to it because this is the line angle structure. In the presence of a strong oxidizing agent, such as the one shown here, it will be oxidized by removing this hydrogen and converting this OH into a carbon-oxygen double bond. So that's the product. You should be able to predict the product if given the reactant and the reagents. Here's another example. Notice this is the carbon that has the OH group. It has no hydrogens bonded to it. So therefore, in the presence of a strong oxidizing agent, as shown here, no reaction or no oxidation that will be carried out. Here's a practical example of the use of oxidation reactions. Ethanol, it's a primary alcohol. In the presence of sodium dichromate or potassium dichromate, which has a reddish orange color. Of course, we have sulfuric acid and water, a strong oxidizing agent right here. That mixture, same as before, is an oxidizing agent. But the main aspect here is this is reddish orange. After the reaction is done, the ethanol is converted to acetic acid, and the other inorganic product is green. So we know a reaction takes place because there's a color change from reddish orange for the oxidizing agent, and when the reaction is done, it turns green. So that's important because this color change is an indication that ethanol was present and it was oxidized. This is the basis for the breathalyzer test that's done on individuals that are suspected of having a high concentration of alcohol. So this is how it works. The individual breathes into this apparatus. Notice the color here is green, which means that it has, notice the color here is green, but originally it was reddish orange. It was reddish orange right here. So as the individual breathes in, if it changes color to green, that means that this individual here, the alcohol or the ethanol concentration was pretty high, so it's been oxidized using the sodium dichromate, and there is a color change. So this is strong indication that this individual here had a alcohol concentration in their breath that was pretty high. So that's what's used in the test for individuals driving on the road. Practical application of oxidation reactions. Let us look at another functional group here, and that is ethers. The ether functionality is an oxygen that's bonded to an R group and another R group. Similar to alcohols, but instead of an OH, we have two R groups bonded. The simplest one here is, of course, this ether, where here's the oxygen and two methyl groups, CH3 and CH3. That's the model, using the molecular model. But here is the CH3 bonded to the oxygen and CH3. So that's an ether. Here's another example. Here's the oxygen, and this case here is an ethyl group bonded to another ethyl group, as drawn out using the model set, or we can just write CH2 bonded to oxygen and bonded to another CH2. We'll give the name in a second. So in terms of the nomenclature, let's look at here at the nomenclature. How do we name ethers? The naming is pretty simple. We name the alkyl groups that are bonded to oxygen and just add the word ether. So we name the alkyl groups that are bonded to oxygen and just add the word ether afterwards. So let's look at this molecule. Here's the oxygen. Here we have CH2CH3, which is an ethyl, bonded to this same oxygen is a CH2, CH3, and this is an ethyl also. Why ethyl? Because we learned that hydrocarbons that have two carbons are named as ethane. And of course, if it's a part of a naming system, it becomes ethyl. So the name of this ether now becomes diethyl, and the word ether is added. So fairly simple. Just identify the groups bonded to the oxygen. Let's apply that over here. Here's the oxygen. It has a methyl here. Why methyl? Because it has just one carbon. It has here a cyclohexyl. Why cyclohexyl? We have 6 carbons here, and it's in a ring. So it's a cyclohexyl. So that's a cyclohexyl and a methyl that's bonded to the oxygen. How do we name that? Since C comes before M, we start with cyclohexyl, then we add methyl, and lastly the word ether. So just use that for your naming system for ethers. Cyclic ethers. As you can imagine here, it's possible to have the oxygen as part of a ring. So here is the oxygen, here's the alkyl group, here's another alkyl group, but they are bonded together in a ring. The simplest, of course, is a 3-membered ring as shown here. The name of this is ethylene oxide. The naming of cyclic oxide is a little tricky, so we tend to use common names for cyclic ethers. Cyclic ethers, again, they have the oxygen as part of a ring. So here's another one. Oxygen, here's an alkyl group, and here's another alkyl group, but it's part of a ring system. This is known as tetrahydrofuran, THF. It's a solvent. This molecule here, ethylene oxide, as you can see here, it's a very useful chemical in the chemical industry. It's used as a fumigant for food stuff, textiles, and other sterilization uses. So they're very important chemicals, cyclic ethers. Let's look at the physical properties. Remember here, physical properties means that they are measurable or observable characteristics of molecules. But first, let's look at the structure and what would affect the physical properties. Because ethers contain hydrogens that are not bonded to the electronegative atom, oxygen. So therefore, this bond here is not a polar covalent bond. Not. So we cannot put partially positive and partially negative here. The only covalent bond, the only polar covalent bond that's present is right here. So we have oxygen being more electronegative than carbon. So therefore this is partially negative and this carbon is partially positive. However, the electronegativity difference between carbon and oxygen is pretty small. If you look at the periodic table, you'll see that carbon and oxygen are very close to each other. So therefore, the interaction here, called dipole-dipole interaction, is very weak. So the intermolecular attractions between two molecules of ether is very small. The intermolecular attraction between two molecules of ether, that interaction is very small. Here's just another way of illustrating it. Here's the molecule, same as here. Here's the interaction that's drawn, and here's another molecule. So the point is that this interaction here, as illustrated by that dotted line, is very weak. Why is that so important? Because if we need to boil a liquid, we need to break those intermolecular attractions. We need energy. You may recall that ethanol has a high boiling point, 78 degrees C. Why? Because, let's draw it out, CH3, CH2OH. Because this hydrogen is bonded to the very electronegative oxygen, making this partially negative and this partially positive. If there is another molecule of ethanol, as shown here, there is a very strong interaction here because this is partially negative and this is partially positive. This is the hydrogen bond. A very strong bond. So in boiling, the energy supplied will have to break this bond so that this molecule can go into the vapor phase. Requires energy. As a result, the boiling point of ethanol is pretty high. As we have discussed, the interaction that exists for dimethyl ether is pretty weak. So therefore the boiling point is pretty low, minus 24. Note again, these two molecules, they have the same molecular weight. But the interaction between, or should I say the intermolecular interaction between these two molecules, they're different. The one that exists for ethanol is strong hydrogen bonding. The one that exists for dimethyl ether is not hydrogen bonding, but very weak dipole-dipole interaction. As a result, the energy required to break the very weak dipole-dipole interaction for dimethyl ether is less, so therefore the boiling point here is low compared to that of ethanol, which has a very strong hydrogen bonding. Let us look at another type molecule called thiols. As a functional group, it has, instead of the OH, it has the SH. So instead of having an oxygen, it has a sulfur. You look at the periodic table, sulfur is below oxygen on the periodic table. So in terms of the IUPAC naming of thiols, again fairly simple. It's similar to that of alcohols. So what we do here is we include the entire name of the alkane. So that's based on the number of carbons, and we just add thiols after it. So we have the entire name of the alkane and just add thiols. What's stated here is we keep the E and add thiols. So let's look at this molecule here. Here's the thiol functionality, SH. So this is carbon number 1 and this is carbon number 2. So this group here is an ethyl. So the name would be ethane. So this would be the root name. So we keep this E and just add thiol. One word. So the name is ethane thiol. This is again a thiol because of the SH. So in terms of naming it, this is carbon number 1, carbon number 2, and carbon number 3. So it becomes a propane thiol. There is a methyl group here on carbon number 2, so it becomes 2-methyl. Of course, there's a 1 here to indicate the presence of the thiol. The next slide has another example. So you start numbering from the end closest to the SH. So these two molecules are the same. So here is the SH. So the question now is, do we start numbering from this end or from this end? The rule states that we start numbering from the end closest to the functional group here, the SH, and not the branch. So we start numbering here. So this is 1, 2, 3, 4, 5, and 6. So it becomes a hexane, and we add the word thiol. The thiol functionality here is on carbon number 3, so we have to indicate a 3 right here. It has a branch methyl group on number 5, so we'll have to indicate 5-methyl. So this becomes the IUPAC name of this molecule here. Same approach. So now you can see why this system of nomenclature is called the systematic way of naming molecules, because the rules are similar for molecules with different functionality. Let's look at the properties of thiols. Most that have low molecular weight have a particular odor, a stench to it. Foul odor. You don't want to get close to it. They are responsible for the odor in rotten eggs and sewage as shown here. In fact, a thiol is added to natural gas so that whenever there's a leakage, what you smell is not the natural gas, but it is the thiol that's added to it, so we can detect a leakage because of that foul, distinct odor. Here's another example. The scent of skunks. Of course, as we know, we don't want to get near to a skunk because it ejects a chemical that's very foul smelling. It's really thiols. And here they are. As you can see, you can name these. So this is 1, 2, 3, and 4. So it's a butane thiol. The thiol group here is on carbon number 1. So it's 1-butane thiol. And there's a methyl group on number 3. So it's 3-methyl butane thiol. Here's another one that's a little different because it has a double bond, but we still start numbering from the end closest to the functional group. 1, 2, 3, and 4. So it becomes butane thiol. However, there's a functional group here, an alkene. Notice ene. So we change that butane to an butene. And of course the double bond is on carbon number 2. So it's 2-butene, 1-thiol. We just break it up to indicate the other functional group that is present, which is an alkene. Notice again, very systematic. So it's a systematic way of naming molecules, and the same systematic way is used to name molecules that have other functionalities. So let us look here at the notice inter here means across, intermolecular attractions, to see if the boiling points will be affected here. So again, sulfur is electronegative, but it is not as electronegative as oxygen. You may recall from looking at the periodic table that fluorine is the most electronegative atom. It is to the extreme top right of your periodic table. So sulfur is below it and to the left of it, so it's not very electronegative. So because it's not very electronegative, the hydrogen that's bonded to it is not very positive. So in other words, this bond here is not a very polar covalent bond. It is polar, but not very polar. So this interaction here in the form of a hydrogen bond is very weak. Extremely weak, at least compared to that if it were an oxygen. So here is a thiol molecule. Here is another thiol molecule. 2. The intermolecular attractions, or the attraction that exists between two molecules, is the hydrogen bonding, but it's weak. So if we were to separate this or supply enough energy to break that intermolecular attraction, it would not be a lot of energy, at least compared to that if it were an alcohol. So the bottom line is that methane thiol, which has just about the same molecular weight as methanol, has a much lower boiling point than methanol. And of course the comparison goes through for the thiols compared to the alcohols. So the thiols and alcohol, doing a comparison on the boiling point for the thiols are less than that of the boiling point for the alcohols, as you can see here. And that's based on the energy required to break the intermolecular forces or attractions between these two molecules. Let us look at the reactions of thiols. First, the acidity. Thiols are weak acids. Remember again, acids here are hydrogens or proton donors. The pKa here reflects the acidity of molecules or of acids. The pKa, or the equilibrium constant. It's around 10. That number doesn't mean a whole lot unless you have a reference point. The pKa of water is about 15, and the pKa of thiols is 10, as shown here. You may recall that the more negative the pKa, the more acidic is that molecule. So, bottom line is that thiols are more acidic than water. The acidity is comparable to, as shown here, to that of phenols that we discussed earlier. So that means that in the presence of sodium hydroxide, this H for thiols can react with this OH from the sodium hydroxide to produce water, and what's left behind is the salt, sodium, as you can see here, salt. Of course, you may recall from Gen Chem, the reaction between an acid and a base gives a salt and water. A salt here is defined as a compound that is ionic, a positive and a negative. So that is the reaction of thiols with a base, the removal of the hydrogen that's bonded to sulfur. Notice it's not any of these hydrogens here, but the hydrogen that's bonded to sulfur is acidic. Another type reaction is the oxidation. We won't get into much details here, but the oxidation and the important oxidation reaction is in the biological system, where the thiols are oxidized to the disulfide bonds. Disulfide bonds. This can be accomplished readily in oxygen. So whenever we have thiols, we have to exercise extreme care in protecting it from oxygen during storage. As I mentioned, the disulfide bond is easily formed from thiols by oxidation. As you can see here, here's the thiol with the SH, here's the H again. Based on oxidation, it is removed. So notice there are no H's that are bonded to sulfur. So therefore that is an oxidation, and this is a disulfide functionality, or an oxidized thiol. As I mentioned, it's very important in the biological system. So this is a particular amino acid known as cysteine. During the process of oxidation, here's a cysteine molecule, here's one, and here's another one. It has the SH and the SH. During the oxidation process, this H is lost and this H is lost to give here the disulfide bond as shown here. Because as you will recall from your course in biology, this gives the cysteine oxidized form, and this is the cysteine reduced form as shown here. So that's one of the practical applications of the oxidation reactions of thiols. So let's recap and conclude. Methane, of course you know methane is CH4. That's a gas that's readily obtained from fossil fuels, or we can use coal in the process of oxidation, and this is the symbol that's typically used to represent oxidation. We can get carbon monoxide. So again, you burn coal, we all know that. We burn coal in the presence of oxygen. We do get carbon monoxide. And of course carbon dioxide, but we get carbon monoxide also. If carbon monoxide reacts with hydrogen, we can get methanol. Of course, as you know, methanol is a very important compound and used as a fuel. Methanol can be further, can react with carbon monoxide in the presence of a catalyst to give acetic acid. And as you know, acetic acid is very important as vinegar in flavoring for salad dressing, etc. And of course, we can carry out another oxidation reaction on methanol to give formaldehyde. Formaldehyde, as you may recall from biology, is that chemical that's used to preserve organs and various biological organs that are shown in the bottles in the biology lab. Here's another molecule, ethylene. CH2, or ethene, because of the double bond. Again, another molecule that's readily obtained from fossil fuel. Here's a reaction that we're familiar with, the hydration, the reaction with water in the presence of a catalyst acid. We can get ethanol. Ethanol again is another molecule used as a fuel. In the presence of acid and heat, we can get diethyl ether, and that's a very common solvent that's used in the organic lab. Or ethylene can react with oxygen to form ethylene oxide, a cyclic ether. In the presence of water and catalyst, we can get ethylene glycol, and of course, as you know, ethylene glycol is also known as antifreeze. So this gives you an idea of how these simple molecules that are obtained from fossil fuels can be converted into important, useful, everyday chemicals. Lastly, here's another one, propene, 3 carbons, 1, 2, and 3. But important here, it's a double bond. This propene is again readily obtained from fossil fuel during the distillation process. And it's very essential in the manufacture and chemical industry, because propene can be converted into the cyclic epoxide, and several steps will give you epoxy glue or resin. So your typical crazy glue is basically an epoxide made from a compound like this. Similarly, propene can react with water, hydration, addition of water in the presence of a catalyst to give isopropyl alcohol. You may recognize this as rubbing alcohol. So that's one way of making isopropyl alcohol or rubbing alcohol, and as we know, that's very useful in everyday life as a solvent and as a disinfectant also. And of course, another way here is we can convert propene into glycerol. Notice we have here a bunch of OHs bonded to these carbons. And that's glycerol, of course, as you know, that's often used in the flavoring and manufacturing food industry, I should say, food industry for glycerol. I think this is our last slide. So this is the end of chapter 14. So once again, I want you guys to follow along in your textbook, work the problems that are given, and take your time and follow through with the concepts that are presented here, and make sure you can apply these concepts to solving different problems. So remember that we are scientists here, and part of the job of a scientist is to come up with creative solutions to problems. Believe it or not, these creative solutions that we devise are basically nurtured and gained or developed through courses like this, using our critical and analytical thinking and applying it to different problems. So continue to study hard, and I will have more information for you regarding the quiz and exam that's coming up. Okay?